So this section is on the Foucault Pendulum, and here we're going to look at why the plane of oscillation of a pendulum rotates. It rotates according to the angular velocity of the Earth and the latitude that the pendulum is hanging at. This coordinate system, this prime coordinate system, is fixed attached to the Earth. The z prime point's perpendicular to the local point on the Earth where the pendulum is hanging. Y prime, say, points north, and x prime points east, say, as we've been doing. And so you can see a little bit of this picture. We have a very long pendulum, and so we're going to use the small angle approximation. Here's my pendulum bob down at the bottom, and because the string is really long, we're going to at some point approximate that it's just moving the x prime y prime plane, and it's not arcing upwards. That's part of the small angle approximation. Here's the local gravity force acting on it vertically downward. Here's the tension. At some point we're going to break these up into components, and so, but first we can just look at Newton's law, Newton's second law, written from an inertial frame point of view, just as we've done with most of these cases, and we just say the sum of the forces equals the mass times the acceleration. For now, the only forces we see, at least an inertial observer would see, is the weight and the tension, and we'll come back to those in a second, and that's equal to the mass times the acceleration in the inertial frame. But as we've done before, if we want to express those in coordinate system of the non-inertial frame, the rotating frame, we have all these extra terms. Ma prime is the acceleration in the rotating frame. M omega dot cross r prime is the transverse acceleration, and since our omega is constant, this guy is 0. Here's the Coriolis term here, 2m omega cross v prime. The next term is the centripetal term, which when you're doing a fixed axis attached to the Earth system, this one's usually neglected because omega is small and this has an omega squared in it, and so we drop the omega squared terms in those cases almost always, and as you'll see later, omega squared will come up again in this problem, and we'll drop it then too. And finally, ma0 is the acceleration of our prime coordinate system in the as it rotates the center of the Earth. And so if we break the sum of the forces down into what they are, the forces acting on the bob are the tension and gravity, the gravity for a stationary Earth, but we combine that with just like we did with the plumb bob for the acceleration of my coordinate system, and we combine those and get sort of a local gravity, and that's what the mg up that you see acting on the bob is. And so we get that term, and then we get a Coriolis term, which we moved over from the right-hand side, and so now we can call this the Coriolis force. We've moved it over to the force side of the equation. It equals mass times the acceleration in the prime frame, or just mr double dot. There should be a prime on that r there. Those two are the same thing. And so, again, the v prime is just r dot prime, right? It's just the first derivative, whereas the acceleration is the second derivative. And so our equation looks like this. Our equation of motion for the plumb bob is the tension plus the weight minus 2m omega cross r dot prime is equal to mr double dot prime. And so that's our basic. This is the thing that's going to tell us how this plumb bob moves, and that's where all the action is, so to speak. And as with projectile motion, the next step is we're going to break this thing down, this equation down into components, x double dot prime, y double dot prime, and z double dot prime, and so on. Those are the second derivatives, but we'll have the first derivatives and just x prime, y prime, z prime, and we'll see how that gives us a rotating axis, a rotating plane for the pendulum. So first, let's just look at the coordinate system here. This is my z prime axis, this is my x prime axis, this is my y prime axis. If we want to start breaking things down into components, let's just look at the tension for a minute. The tension in the x direction is always bringing the pendulum bob back in the direction of the origin, right? Tx is pushing back towards the y-axis, ty is pushing back towards the x-axis. And so the tension is minus Tx, which is the x component, I hat prime, minus Ty, j hat prime. That's a component representation of T. Note that L is very large, and the maximum angle is very small. And so you can almost, even though the drawing doesn't show it, you can almost say that the pendulum bob is just hanging straight down. And so the magnitude of the tension is approximately equal to the weight. And so the x component is just the cosine of this angle, the angle that the pendulum makes with the line connecting the pendulum, the perpendicular line connecting the pendulum to the y-axis. And so it's just x prime over L times gravity. That's the magnitude of the x component. Similarly, the magnitude of the y component is y prime over L times mgy. It's just the cosine of this angle times the tension, or in this case the cosine, in the y case the cosine of this angle over here times the tension. And so you can write the tension as minus mgl x prime over L, minus mg x prime over L I hat, this should be an I hat prime, minus mg y prime over L j hat prime. So we broke down the tension. Once again, we're trying to cast all of our equation in component form, and the next term from the first screen we looked at is the Coriolis force. And so we're going to break the Coriolis force down into components, and that's just what we've done a whole bunch of times. It's just this term minus 2m omega cross r dot prime, and that's we can write the cross product this way. And a couple of things to notice here. First of all, since we're using the small angle approximation, we're going to assume there's no velocity in the z direction of the pendulum bob. We're just going to assume it's moving the x prime y prime plane. Furthermore, we're going to pick our y prime axis point north and our k prime axis pointing vertically, and so there's no component of the rotation along the x prime axis. And so, as we've done in previous problems, our equation is going to have a 0 here and a 0 here. And so we end up with this. If we work this cross product out, we get this term. We get I hat prime times the cross of these two, which gives it's omega cosine lambda times 0 minus y dot prime omega sine lambda, and that's what you see here. And I've done the same thing for the j and the k. And then I've cleaned up the math a little bit, and so this is our answer, and we get a y prime minus y prime omega sine lambda times I hat prime plus x prime dot omega cosine lambda j hat dot minus, and this is the third guy, which is that's an x dot prime cosine lambda k hat prime. And we're going to neglect the k hat prime term because we're only interested in what's happening in the xy plane, and this guy is only going to affect the weight of the pendulum bob, and it's going to be a very tiny effect, like 0.1% or something like that, and so we'll be able to let this guy go as well. So this is the equation we're trying to break down into component form, and we broke down this term and this term. This one's pretty easy, the mg term, because it just points in the negative k hat prime direction. And so now we can look at the x components, and we can say, look, mx double dot prime is equal to minus tx plus the term that came out of the Coriolis force in the I hat direction, right? And if we simplify that, the minus tx becomes minus x prime over L mg plus 2m y dot prime omega sine lambda. And so and we can do the same thing for the y. And just to be clear, if you look at these two equations, this is the equation in x and this is the equation in y. If you drop the Coriolis terms, right, then you just get back to a simple harmonic oscillator. And so there's a lot to learn from these two equations. One is the greater the y acceleration is, the greater the y velocity. So if the thing is oscillating along the y plane, it gets a large boost in its x acceleration. And similarly, if the thing is it gets its largest boost, I should say. So if its y velocity, when its y velocity is greatest, it's having the most influence on the x acceleration. When its x velocity is greatest, it's having the most influence on the y acceleration. So you should be able to sort of see that that's what's kind of causing this thing to turn, even though there's no proof in that statement, but you should be able to see that. So it says, notice that the y velocity affects the x motion and the x velocity affects the y motion. This is called coupled equations. This is hard to solve differential equations wise, because the y's are connected to these two differential equations are called coupled. And that's a common problem in sort of more sophisticated physics problems. And so what we're going to do is kind of show via a little bit of trickiness that this leads to a pendulum that is rotating, that has a rotating plane of oscillation. And what we're going to do is we're going to recast these equations in a coordinate system that's actually turning, and show that that produces, if we pick the right angular velocity for the coordinate system to turn, it gives no, it removes the coupling of these equations. So this is where things get a little interesting. Omega prime is just omega sine lambda. This is the component of the Earth's angular velocity about the z-axis. This is the thing we're kind of that's kind of gives the angular velocity of the plane of the pendulum bob. And so just for simplicity, we're going to write that as omega prime. And what we're going to do is we're going to choose a new coordinate system. So we have our original x prime, y prime, z prime coordinate system that's fixed to the Earth. And now we're going to choose a coordinate system x, y, z with the same z-axis, but this guy is going to be sort of counter-rotating with the Earth at this velocity. And so we're going to write our x prime related to the x coordinate system as it's equal to x cosine omega t plus y, x cosine omega prime t plus y sine omega prime t, and then y prime is minus x sine omega prime t plus y cosine omega prime t. This is just a transformation between these two coordinate systems, one that's rotating with angular velocity omega prime t, and the other one that isn't. And so we're just looking inside that one coordinate system. And so now what we're going to do is we're going to say, okay, here's our relationship between x prime and y prime and x and y. And so we're going to take the first derivative, and we're going to calculate x prime and y prime, and then x double prime and y double prime. And so if you take the derivative of let's just look at the x prime case. If we take the time derivative, the derivative with respect to time of the right-hand side, you get x prime cosine omega prime t minus omega prime x sine omega prime t. So that's just taking the derivative of this piece, right? It's the derivative of the first times the second plus the derivative of the second times the first, and that's what gives you the first two terms here. Then you do it for the second term, the y sine omega prime t, and that's what you get over here. And so that gives you the first derivative, right, for x. And then you have to do the second derivative, so you got to take the whole thing all over again, and instead of you go from 2 terms to 4 terms, now you go from 4 terms to 8 terms. And so you can just check these. I've done the first derivative of these two guys. So this guy gives me 2 terms, that's these two. This guy gives me the 2 terms, that's these two. The y prime sine omega prime t gives me the last 2 terms on this line, and then the last term for the first derivative gives me the 2 terms that are written just below that are also part of that equation for x double prime. X double dot prime. And then, as has been our practice, we drop out the terms that have omega prime, omega squared in them, omega prime squared in them, because they're just really small. And so, and then, if you'll notice, the second and third term are the same, so they just add. Same way with the second to the last and the last terms, they just add. So I end up with 1, 2, 3, 4 terms that give me x double dot prime in terms of x and y and their derivatives. And so now I can do the same thing for y, by the way, and it'll look very similar. So here I am doing the same thing for the y prime dot and y prime double dot. It comes out very similar to the way the x's did, the x primes did. And I get an equation for y prime double dot in terms of x's and y's, just like I did for the x prime double dot. And now we're going to return to our equation from our equations of motion. This is our component equation here for x double dot prime, and if you go back a couple of screens you'll see that it was minus g over L times x prime plus 2, well, before it was written omega sine lambda, but here I just have omega prime, which is the same thing as omega sine lambda, times y prime. And now for this equation we're going to substitute in what we had for the cosine, for x double dot prime in terms of the x's, and in each of these cases we're going to replace it with their dependence on the x variables rather than on the prime variables. We're going to use the unprimed variables, and so the left-hand side becomes the equation from the previous page, and the right-hand side, similarly, I've substituted in. I have the minus g over L times my equation for x prime in terms of the unprimed variables, and my similarly for the y prime in terms of the unprimed variables. And there are a few things you can see. First of all, the red lines are terms that cancel, and similarly the two terms with red arrows cancel, just additively they cancel. The two terms with single green arrows cancel each other, and the two terms with green double arrows cancel each other. And so the equations simplify considerably, and I get x, I no longer have the primes, right? X double dot cosine omega prime t plus y double dot sine omega prime t equals minus g over L x cosine omega prime t minus g over L y sine omega prime t. And so that's a pretty simple equation compared to what we were wrestling with just a few minutes ago. So now if I rearrange this equation, I get this. I get x double dot plus g over Lx cosine omega prime t plus y double prime plus g over Ly sine omega prime t equals 0. Notice that cosine omega t and sine omega t, time is just continuous, and so they're not 0, at least not at all times, just at individual points. And so in order for this to be true, I have to have both this equation and this equation be true. Which means which decouples the equations in x and y and shows that that in this rotating frame that rotates at sine omega prime t, the oscillation is stationary, and so this sine omega prime t is this omega prime t is the angular velocity of the plane that the pendulum is rotating in.